All right, guys, today we're going to be talking about the life cycle of a star. And as we move through this, just understand that stars are really not considered living because they're not made out of cells, have DNA, or reproduce. But they do go through stages and can be created and destroyed. So therefore, we just call it a life cycle. Here is an overview of the life cycle of a star, and we are going to be going through the different phases. So the very first thing you need to know, regardless of a star's mass, is that all stars do depend on their mass, but they're all going to be created in a nebula. The definition of a nebula is a giant cloud of gas and dust that is being held together by gravity. And that gravity is that gravitational force. So here's a picture of a nebula. In my opinion, when you look at pictures of space, they are the most beautiful images. But it is this dense area of gas and dust. And then as the stars start to come together, they'll start to pulse. And then more gas and dust will condense. And then the larger it comes, the stronger the gravitational pull will get. And eventually, a star will be created. Now, the path that a star goes through does depend on its mass. And that is extremely important for you to understand. So put a big star by that in your C notes. And we know that when we do talk about a nebula, there obviously is going to be lots of heat and pressure as that gas and dust is pulsing, and this is where a star is born. So let's talk about a protostar. A protostar is like an infant or a baby star, if you will. It is a star that is forming. They are extremely unstable, and they're actually not large enough to to get equilibrium. But the reason why a protostar is not considered a star is because it does not do nuclear fusion. Nuclear fusion only occurs when the mass is high enough. This is where it does take those two hydrogen atoms and push them together to create helium. Take two helium atoms and push it together to create carbon. This is what allows all stars in the universe to create light and heat. So if it does not give off light and heat, it is not considered a star yet. So we call it a protostar. Just a little bit of extra, little tidbit of information, what I almost gave away in class earlier. If the mass of the star does not meet that critical point where it can reach equilibrium, the temperature of the core is not going to be reached, and it almost is kind of like it dies before it's even created. And this is what we call a brown dwarf. Jupiter is actually an example of a star that failed. Now, to us, Jupiter is a planet, right? It's the largest planet in our solar system, and it's considered a gas giant. But really, Jupiter was actually intended to be a star, but the mass was too small that the core couldn't reach that maximum temperature to create nuclear fusion. So they do not glow and produce light. They can only reflect it like other planets and moons. So let's talk about the overall goal of a star. The overall goal of every star is to maintain that equilibrium, kind of like homeostasis in a human body. In a stable star, the gas is going to be pushing out from the center, but the gravity is going to be pulling in. And so you want these two forces to be balanced. Therefore, it can remain equilibrium. When the forces become unbalanced is when interesting and disastrous things occur. So what do you think determines the length of the star? Well, remember how I said mass was extremely important? Mass is it. So my analogy for this is, let's think of a Hummer and a VW Bug. Hummers are huge, but they get awful gas mileage. Because they are so large, it takes a lot of energy to maintain the Hummer, where a VW Bug is very small, quick, and efficient, so it gets a lot better gas mileage. Stars are the exact same way. A really big, massive star is going to burn through its energy or its hydrogen a lot faster. So therefore, it's not going to have a very short life at all. Maybe a couple million years, which is really short for a star. Small average stars because they are smaller in size, are not going to require as much energy to maintain, and therefore they can live much longer, to billions and billions of years. So if a star does have small mass, that means it takes fewer atoms to meet that equilibrium. If it takes a larger mass, that means it takes more, and again, that's why it does run out of energy faster. So let's talk about the main sequence. When we get into the HR diagram, you're going to understand what this means. But just know that most stars spend 90% of their life as a main sequence, kind of like what we do as an adult. So here we're kind of making an analogy of a protostar to a fetus, where over here in the main sequence, you can go from being a new, bright, blue, beautiful star to an older yellow star. So we know that stars are created mainly from hydrogen. As a star ages, it's turning that hydrogen into helium through nuclear fusion. Its temperature is going to decrease, and because its temperature decreases, the color of the star is going to change. And there are predictable stages that the star will go through in the main sequence. But it is where most stars spend 90% of their life. Like our sun is in the main sequence right now and has been for the last millions of years. So we know a star is just really nothing but a big hot ball of gas, mainly hydrogen, and that's turning that hydrogen into helium at its core, which is nuclear fusion, again allowing us to have heat and light. So generally, the hotter the star is, the brighter the star is. And so my analogy is like, let's think about when you turn 18 and you're officially considered an adult. You're bright, you're hot, you're ready to tackle on that world. Well, as you get older and you go kind of get right back to becoming a senior citizen, you're not as hot, you're not as bright, maybe dementia setting in. So kind of just go with that analogy on stars. So the main sequence can take the form of blue giants, which are huge stars, hence the name giant, all the way to sun-like stars, which are considered average, to even red dwarfs, where dwarf, imagine, means it's very small. So that's kind of how they classify stars, or by their size, again, their mass. You have your giants, your supergiants, your average, and your dwarfs. So let's talk about a blue giant. No, this is not the sun with a different color. This is a blue star. Blue giants are any stars that are going to be about 3 to 40 times the mass of the sun, because we do use our star, which is named the sun, as one mass. Everything is going to be relevant to that. They do produce a high amount of energy, but at the same time, they have very short lives because they go through that fuel so much faster. There are many other stars out there, and eventually we will get to the supergiants, so we'll just hold fast. Superstars, or huge stars, can be anywhere to 1.5 to 3 times the mass of our sun, but they're still not going to be considered giants just yet. So let's talk about average size, like our sun. They're going to be anywhere from the exact same size, or maybe about 1.5 times the mass. They can live anywhere from about 9 to 8 to 10 billion years. Our sun currently is exactly around halfway through its life cycle, and is what they estimate to be 5 billion years old, based on where it is in the main sequence and its core temperature. So let's talk about red dwarfs. As the name implies, they are small and they are the color red. And you're going to learn that the color of the star can indicate the temperature. And it's actually opposite of what you would think. Everybody tends to think, because of our society, we deem red as hot and blue as cold. But in reality, think of the flame test that we did a week or so ago. We know that when the temperature of the flame changes, the color is going to change. Stars are the exact same way. And red happens to be the coolest of all the colors. So red dwarfs do have less mass than our sun because they are smaller. They have low energy, and therefore they will live the longest. And they are the most frequent because, as you can imagine, if you're going to live for 30 to 50 billion years, you're going to outlast all the other colors and sizes. So let's talk about exactly what's happening in nuclear fusion. You take your 4 hydrogen plus a lot of heat and pressure, and you're going to make 2 helium with a burst of light on the side. Thank you for the light. These stars, when they start running out of hydrogen in their core, they're going to have to go to the next best thing, which is helium. It takes a lot higher temperature to burn helium, and so therefore the core has to heat up. As it heats up, this causes things to expand, because we know, due to convection, right, that when things heat up, they expand, therefore causing them to rise. Well, you're in space, so you're not going to rise. They're just going to expand. And this is what can give us some of our supergiants. So here are some names of some real stars. Here's Betelgeuse. Betelgeuse is this red supergiant that is so big I couldn't even fit it in my picture, compared to Regal, Sirius, Sol. These are all comparisons of all the different types of stars and all their different sizes. But Betelgeuse is a red supergiant. So kind of like where I talked about a giant, a supergiant is going to be the largest classification of stars that we have. So let's look at this picture. This tiny little bitty dot right here is our sun, or is Jupiter. Sorry, this is Jupiter. Here's our sun. Now to us, the sun seems huge. In fact, the sun is so big that you can actually feel 1 million Earths inside the sun. So we're going to let that sink in for a second. 1 million Earths. But yet, look at the size of our sun compared to Sirius, compared to Pollux, compared to Arcturus. It is so small. It just seems so much closer to us, or larger to us, because it is so close compared to all the other stars in the universe. And so these are some examples of red giants. So let's talk about what happens when a star dies. Again, it goes to that mass on what phase it's going through. But when a star actually starts to leave that main sequence, it's either going to become a red giant, if it's an average size or smaller, or it's going to become a supergiant if it's already a giant. So no matter what, when a star leaves a main sequence, it is going to expand. And we now know the reason why a star expands is because it has run out of hydrogen gas, and it's had to revert to helium, requiring the core to burn at a higher temperature, and so the star does expand, meaning the gravity also gets weaker. So average become giants, giants become supergiants. So like I said, we run out of hydrogen, then they start fusing that helium into carbon, and then carbon can fuse into iron, which is causing the gravitational force to weaken and expand, allowing the star to get bigger. And then cooler. So we tend to think that larger stars are hotter, but again, it's the color directly related to the temperature. Because you still have so much energy and I spread it in a big room, it's not going to feel as hot. And so the energy is actually less compared to a smaller condensed area. So let's review what we've talked about so far. Regardless of what type or size of star you are, you begin your life in a stellar nebula. You can then either be an average size, like our sun, and stay in the main sequence, where you spend 90% of your life. Then you're going to move on to the red giant phase. This is like your senior citizen, as you can see right here. This is where you're no longer considered an adult, you get the blue plate special, you're getting older, you've ran out of hydrogen. If you're a massive star, you still spend 90% of your life in the main sequence, but now when you run out of hydrogen, you expand even more and become a red supergiant. So let's talk about what red supergiants will eventually become. Well, they are the ones, and the only ones, that will explode into what is known as a supernova. Isn't that beautiful? So a supernova is a giant, powerful explosion when only the largest stars finally run out of fuel at the core and the pressure can no longer maintain equilibrium. It will explode. So the explosion of a star that has reached the end of its life. Little fun fact is there is about one supernova every 50 to 100 years in the Milky Way. But because the Milky Way is just a galaxy and among many, 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 there's actually a supernova every second somewhere in the universe. So let's talk about the death of the star. If you are a big supergiant, after the supernova, you have three choices. You can become a black hole. Due to the incredible mass and the fact that matter is collapsing in on itself, it actually reverts backwards and creates a gravitational force so strong that not even light can escape. So only the most massive of massive of massive stars will become a black hole. So is our sun going to become a black hole? No, it's not. Then there is the planetary nebula. Make sure you do add that word planetary nebula so you do not confuse it with the stellar nebula. Then because it does explode, it does put off all that gas that it wasn't using out in there. And that is where more stars can come from to recycle itself. And then a neutron star, which if it spins is called a pulsar, is when the outer shell of the star explodes into a nebula, but then the remaining core collapses within itself, and it creates a star that is so dense that only protons and neutrons are combined, protons and electrons are combined to produce neutrons. Hence why it's called a neutron star. So let's talk about what red giants will be. This is our sun, okay? All those others were the most massive of massive. When our sun becomes a red giant and then it officially runs out of that helium and can't turn it into carbon anymore, it is going to throw out its outer layer and form a nebula. This is what's called a planetary nebula. And then all that's left, so this is a planetary nebula. Isn't it beautiful? Then all that's left is this little white core in the middle, which we call a white dwarf. So the one way you can tell a stellar nebula from a planetary nebula is if you see this little white circle in the middle, then you know that's the death of a star and not the birth of another one. So the core will remain burning white to let you know that it is hotter, until the rest of its life, where eventually it will completely die out and become a black dwarf. So once the core of our sun dies, then it is officially a black dwarf, the dead remaining parts of a sun or a star. So this is what will happen to our sun. When the sun is about 7 billion years old, got about 2 more billion to go, it is going to start to cool and become bigger. Then it will enter into the red giant phase. Eventually it will sit there for a few more million years. It will blow out its outer atmosphere of a planetary nebula, and the core will remain burning until eventually it dies out. So no, our sun will not now nor ever or could ever become a black hole. So what would happen to Earth? This is where our PBL is coming in. The expanding sun is going to actually engulf the Earth just before it reaches the tip of the red giant phase. Once inside the sun's atmosphere, the Earth will collide with particles of gas and our orbit will decay and it will spiral inward. Of course, we know the temperature would be hot enough that life would have died way before that. So in our PBL, we're looking for a new planet. We're looking for that new exoplanet, not because our sun is going to explode, but because our sun is going to be leaving the main sequence and entering into that red giant phase. Okay, so tomorrow we are going to start talking about the life cycle of a star, and you're going to be creating a poster. So if you need to rewind this video, because I know it's a lot of information and a lot of questions. Also, don't feel free to go back on any of these YouTube clips I didn't watch and watch them yourselves. Bye.